We are living in the neighborhood of a star sun. And sun is not a light bulb. Sun is a hydrogen bomb.
Well, of course, everything we do on the Earth and as a human society is affected by our interaction with the sun. The sun supplies not just our heat and light.
The sun is affecting our environment in so many ways. We have started to understand the multitude of processes, how our vulnerable planet is affected.
Continuously streaming from the surface of the sun is this magnetized solar wind. And as it rushes past the Earth, it actually interacts with and deforms the Earth's magnetic field.
This whole research area is grouped under the term space weather.
When the sun is very active, it can deposit a large amount of energy in the Earth's upper atmosphere.
The sun has effects, and then this causes weather in the upper atmosphere.
The atmosphere is a coupled system. All the atmospheric layers transfer energies back and forth between them.
If you want to understand a tiny part here, we have to understand all the interactions which happen in the system formed by sun, space and Earth.
And the middle atmosphere is the least known part of the atmosphere.
The geometry of the Earth's field, basically, is such that the field lines are converging on the poles. So the polar regions are fantastic places to be because a wide area of the magnetosphere is imaged into a very small area of the ionosphere.
In Svalbard and northern regions, the magnetic field is vertical, and we are more directly connected to the sun than anywhere else in the world.
And these high latitudes are unique because it's where the energy from the sun is primarily dumped up here, which is why you only get the aurora over the northern and the southern polar regions.
For 30 years, Eiscat has been studying the upper atmosphere with powerful radars and antennas in 3 different countries.
We are sending radio waves to the upper atmosphere near space in the scale of 2 million watts of radio power. That's a huge power. You could imagine that you have microwave ovens opening their doors. How many microwave ovens would you need to get this 2 million watts to the space?
There are very few facilities in the world where you can do these types of experiments.
Sending 2 million watts, we get 10 to the power minus 18 watts to our receiver. It's a tiny, tiny fraction of the power we send up. And in fact, we can measure simultaneously several parameters like the temperature there, the motions, the winds, the densities of particles.
A lot of people do want to come and use the system. It's one of the best systems in the world.
But why do we need to make these measurements?
You get these huge magnetic storms on the sun which increase the amount of energy coming into the upper atmosphere.
These affect radio communications and GPS signals, satellite signals.
You have a mobile phone, you probably have satellite navigation in your car, you may even have a little handheld satellite navigation if you go off hiking anywhere.
The cause of them is not fully understood.
There's been problems in the past when huge magnetic storms on the sun have caused power stations over northern Canada to completely short out. But you can't predict when a solar storm is going to go off. The more data we can get, then we can hopefully predict these more. And the equivalent now is, obviously we can try and shut the satellites down, put them into a protective mode.
So, predicting space weather will help to keep mobile phones working. But Eiscat can do much more than that.
9. Ignition sequence start. 6, 5, 4, 3.
The astronauts on the Apollo missions really were lucky in their radiation doses. There was a few solar storms that went off, which were kind of a few days either side in some cases when they were up outside the protective shields. Now both America and Europe, China also and Russia are getting into more of the space race, more of the human kind of space race, then we're going to need this information, otherwise you're going to be sending people up there and, you know, they're really going to be struggling with these radiation doses.
Due to the fact that there are so many satellites and increasing all the time, there is a kind of pollution in space, because when they go out of operation, this is still stay there.
Some people say that space debris itself could be a catastrophe, in the sense that the fragments that are already there can begin to collide together, creating smaller and smaller fragments, and the whole thing might be a cascade process that eventually fills the Earth's environment with small fragments and almost denies our access to certain regions of space.
The number of objects in space is increasing all the time. This radar is one of the most powerful instruments that are able to detect these small objects in space. It can be possible even to avoid some catastrophes, you know, by having this knowledge of where these objects are.
Protecting spacecraft and safeguarding the lives of astronauts is important in itself, of course. But what about the rest of us here on planet Earth? How does Eiscat help us?
The climate models in these regions of the world have the biggest uncertainties.
By looking at the upper atmosphere, we can have maybe a 10 times better sensitivity to climate change in studying parameters up there.
The polar regions are extremely important for climate models to have accurate values for predictions far into the future.
If we're going to try and do something about the climate change, then we have to keep the measurement series going to see whether or not what we're doing is working or not.
So measurements of the upper atmosphere can help us understand climate change. But does climate change itself affect the upper atmosphere?
In the lowest part of the atmosphere, there's a greenhouse warming, which is making an expansion of the lowest part of the atmosphere. But when these greenhouse gases diffuse into the middle atmosphere, then they actually act as refrigerants, and the middle atmosphere is actually cooling and therefore shrinking. And the ionosphere is therefore sitting on top of this, and it's occurring progressively lower and lower down. And here's part of the data series. Here we're looking at the height of one of the ionospheric layers. So you can see that the height was fairly constant, if not increasing a little bit, until the end of the 1970s, and around 1978 it started decreasing very distinctly.
The evidence suggests, therefore, that climate change below also influences the very nature and dynamics of the ionosphere. But is there any evidence that human activity is directly affecting the atmosphere this high up?
There is a phenomenon in the mesosphere that occurs at about 80 kilometers of altitude, which are noctilucent clouds produced by very small ice particles. They produce very strong signals in the radar, so they are very easy to observe when they happen. A big question about this phenomenon is to explain why there is water there producing these ice particles and the clouds. And it appears that these clouds were first observed by the end of the 19th century. The reason why we believe that there is water at this altitude is due to the diffusion of methane that is produced here on the surface.
Methane, a significant greenhouse gas, appears to be changing the atmosphere at heights that were previously thought to be unaffected by human activity. So the importance of understanding the upper atmosphere is clear. For radio communications, energy supplies, human health, even climate change. And Eiscat is leading the way to improve this knowledge. But what are the limits for the Eiscat facility?
We don't know, basically, exactly what's going to happen in a certain location. We can say, like I said, there's energy coming from the sun, but we can't say it will happen at this location or it's going to last for this long.
Eiscat has been amazingly successful as an international research facility, but the limitations are clear. Our present systems are based on these large parabolic and cylindrical antennas.
These are big 32, 42 metre dishes and bigger.
We can only do measurements in 2D by swinging the radar back and forth.
Those are capable of only pointing in one direction at once, and they move very slowly.
So it takes a finite amount of time for those to scan across the sky.
But in those 2-3 minutes, there is a lot of change.
So you could be looking in one direction, something suddenly happens behind you.
And our recent measurements show that changes occur on timescales of seconds.
So the next stage of development for Eiscat will be something truly exceptional.
This capability will be unique.
For the first time we will be able to separate time and space and resolve all those fine-scale structures.
This is an exciting opportunity for us.
Eiscat 3D will allow you to look in multiple directions very, very rapidly.
Possible because it will be a phased array.
The next generation of Eiscat, Eiscat 3D, will be more like the Morrow phased array radar over there, capable of either forming multiple simultaneous beams or scanning a single beam very quickly on the order of milliseconds rather than the minutes it takes us to move our existing dishes. But what is astonishing is the scale.
If you would think about an antenna field of 100,000 antennas,
the largest and most sophisticated radar facility ever built. It's a very ambitious project.
The existing antennas in Tromsø are second generation radar. The radar up here is like third generation radar. Americans have built something I would call the fourth generation, and Eiscat 3D will be the fifth generation above everything that currently exists.
In this technological age, this area of space surrounding the Earth is becoming critical to human activity. Understanding those conditions, the space weather, is as important as understanding the weather down here on Earth. What we're doing with Eiscat 3D is trying to build one of the key, the world-leading elements in the chain of instruments and facilities that enable us to understand the behavior of the Earth's environment and predict it. That really is one of the key technological challenges for human society in the 21st century.